So as I promised, I'm going to go through a couple of papers that look at various aspects of CO2 utilization and removal. This one looks at technological and economic prospects. There's another one that looks at biophysical limitations on CO2 sequestration with some of the methods that are commonly suggested or advocated and are supposed to be reliable. So this paper makes some points that are somewhat of a repetition or emphasis on some of the things we have discussed, but it doesn't matter. So it looks at it in a nice carbon cycle sort of way. So it's looking at the stocks. So the atmosphere, this is averaged over 2008 to 2017 period, and looks at the net atmospheric growth over that period of 17 gigaton CO2, and it looks at fluxes from energy, buildings, industry, transport, agriculture, land use change, and uptakes by land sink and ocean sink, and then looks at various pathways with which carbon utilization and removal is possible. Chemicals from CO2 like syngas, for example, fuels from CO2, which also includes so you can think of chemicals maybe as acetone and IPA, isopropyl alcohol, and fuels from CO2. Products from microalgae, which we have mentioned before and looked at the life cycle analysis of Lanzatech, which does microalgae and enzymes and so on. Concrete building materials we mentioned before. CO2 for enhanced oil recovery. Bioenergy with carbon capture and storage, so we always talk about BECCS BECCS. Enhanced weathering, so these are the unusual pathways in that sense. BECCS, enhanced weathering, forestry technique, soil carbon sequestration technique, and biochar. So there are some that are seen as closed pathways, so they take out CO2 and store it, whereas the others are either cycling or open pathways. So you can see the numbers corresponding to this list here with the various stocks or reservoir sizes. So reserves of fossil fuels is estimated at 3100 gigaton CO2. But the resources, which is kind of the optimistic theoretical estimates by geologists, is massive at 45,000 gigaton CO2, whereas you can think of reserves as producible fossil fuels, and these as theoretically available potentially there. Lithosphere and ocean has, of course, sediment. Hydrosphere has a massive reservoir as well. This includes various components of the ocean storage, and of course there is soil and biosphere. So you have to think of CO2 utilization as kind of a displacement which can help reduce emission. So let's say you are using CO2 for enhanced oil recovery, then if you are using more CO2 to push out oil than the CO2 that is released as oil from this process, then you are putting away some CO2. Depends on how long it's going to stay there. So you can draw down from the atmosphere, so remove from the atmosphere but not store it anywhere, so just put it into various things like concrete or polymers and other things. So utilization is not necessarily a solution, especially if it is not stored away for a long time. And as we head towards decarbonization and net zero, things like CO2 for enhanced oil recovery have to begin to phase down, right? So the 10 CO2 utilization removal pathways we looked at already. Chemicals from CO2, so catalytic chemical conversions of CO2 from flue gas or other sources into chemical products. So utilization products involve things like CO2 derived platform chemicals such as methanol, urea, and plastic. So urea is one of the big successful stories, even though you have to be careful in a life cycle analysis whether that is really displacing it for a long enough time. Plastics can store it for a long time. Methanol, of course, depends on what you do with it. If you convert it to other fuel, then you're going to re-release it. Storage and likelihood of release, high and low. So various chemicals, days to decades. So that's the high. Emissions on use or release during storage, so hydrolysis and decomposition. And example cycles here basically corresponds to the various ways in which these are envisioned. For example, CO2 from the atmosphere can be taken up with direct air capture, which is referred to as pathway A, and concentrated into CO2 so that you go from 0.04% to something like 100%, and then it can go to storage in the lithosphere, or it can be transformed into a carbon product. And CO2 from the atmosphere can also be used in land-based capture, like forestry-based approaches, agroforestry and so on. And then there is emissions during use, which is going to put it back. So this is CO2 fuels pathway, and that's the forestry pathway, and this is the CO2 enhanced oil recovery pathway here, carbon in the lithosphere using to produce oil, which is a carbon product which is going to then emit on use. And carbon product also can lead to industrial capture, similar to the CO2 EOR pathway. And storage here in the biosphere, which can be released on maybe some longer time scale unless there is a forest fire which belches it all out back. But carbon product and also go into storage into the carbon in hydrosphere and so on. So these are the various pathways that are envisioned, which are used as example cycles in each case here. So I won't read all of them, so you can go through the paper. Fuels from CO2, catalytic hydrogenation processes to convert CO2 from flue gas or other sources into fuels. So again, you have methanol, methane, and the Fischer Tropsch derived fuels like diesel. So these are various fuels, weeks to months, and likelihood of storage and release is high here. So combustion of fuel and consumption as a bioproduct. So concrete building can lead to emissions during extreme acid conditions, and can actually work as carbonates to sequester for centuries, so the likelihood of release is low. CO2 EOR likelihood is low and sequestration is millennial. Bioenergy with carbon capture and sequestration gets a lot of pushback because you don't know whether that will compete with food production, and how land use will affect emissions, and whether food security will be affected. And of course, we don't have scalable carbon capture and sequestration yet. Nonetheless, bioenergy from crop biomass can be a way to sequester on millennial timescales, and likelihood is considered low. And enhanced weathering, another approach with aqueous carbonate, or you can grind up rocks like olivines and put on croplands and grasslands and forests, and enhanced crop yields can theoretically reduce land use for food production and have other co-benefits in terms of, let's say, reducing emissions from land use. So again, aqueous carbonate for centuries, and the likelihood of release is considered low. Forestry techniques, growth of woody biomass via afforestation, disturbance and combustion or decomposition can re-release it, but the release potential, the storage can be decades to centuries depending on how protected the forests are, but the release potential is high. Soil carbon sequestration, soil organic carbon can be years to decades, but high potential for release. With warming, of course, soil respiration, heterotrophic respiration goes up, soil emissions go up, so disturbance and decomposition is always an issue. Biochar, the life cycle, energy use, etc. have to be done, but black carbon can put away carbon for years to decades, with a high potential for release through decomposition. So again, you can map these example cycles onto this figure, which I didn't do, but you can see here that utilization pathways are represented as combination of steps A to L. Green arrows trace an example of open pathway, which is forestry, so it can through B, F, and G. So that's one pathway as an example. Okay, there are others that you can read through here. So the range estimates of the potential for CO2 utilization and present day break-even cost. So there is technical feasibility issues and economic prospects that one has to remember. So utilization can be either storage through these pathways that we discussed, and the storage time scale is different, and the release potential is different for different pathways, or they can just take it out of the atmosphere but just put it into other products, and the utilization of those products can re-release with various high and low potentials, or they can actually do direct air capture and storage for a long time as well. So again, the idea is that we have to watch out for life cycle analysis kind of approaches to see whether the prospects actually add up to net benefits in terms of either emissions reductions till we transition to decarbonization or actual sequestration. Okay, so there are conventional utilizations with removal potentials in 2050 estimated in terms of millions of tons of CO2 removed per year. Utilization potential in 2050 with the same units and break-even cost of CO2 utilization in 2050 in US dollars per ton of CO2. Obviously, there are many assumptions involved in this, and you can see the various details that go in here. So the pathways, conventional utilization include chemicals, fuels, microalgae, concrete building materials, enhanced recovery, oil recovery, and the non-conventional utilizations here are considered BECCS, enhanced weathering, forestry techniques, land management, and biochar. So the removal potential estimated in 2050 for chemicals 10 to 30. Fuels and microalgae are estimated at 0 by 2050. Basically, you want to be in decarbonization by then also. Concrete buildings have a good high potential in terms of millions of tons of CO2 removed per year. Enhanced oil recovery, again, this estimate assumes that you are going to put away more CO2 than the CO2 that's going to be released from the oil that you are extracting with this method. But as I said before, by the time you want to hit decarbonization, net zero goals, etc., this better be winding down, right? BECCS, despite all the controversies, this paper estimates it at 500 to 5,000 million tons per year. Enhanced weathering at 2,000 to 4,000. Forestry techniques, you can see the range is large in each of these. Land management, 2,300 to 5,300 million tons of CO2 per year, and biochar at 300 to 2,000. The utilization potential, again, this you can think of this as displaced carbon rather than carbon that's taken out of the system. And fuels have utilization potential of 1,000 to 4,200, even though they don't have a removal potential. Microalgae also have utilization potential. Concrete building material have the same number for both, and same for enhanced oil recovery. And the same here for BECCS, but the enhanced weathering is not disclosed here, or whatever that means. I should have looked it up, but sorry, you can look it up for me. Forestry technique, you can see that the utilization potential is much lower than the range of removal potential. Depends on how the forest products are used. There is something called socioeconomic carbon, which talks about carbon that's locked up in various products, whether it's polymers or wood and so on, or concrete even. Land management, again, there is a utilization potential, and similarly for biochar. So here are the break-even costs estimated going from savings two costs, and there are discussions in the paper about how to incentivize these things, and some of the things like biochar and land management, for example, are expected to have higher potential with incentivization, or they're expected to benefit from incentivization, but nonetheless the break-even cost here is negative. It means there is actually a net saving with these methods. Similarly also with forestry techniques. Okay, cost of utilization compared with product costs and scoping review. So all these comparisons have to be some kind of a counterfactual world comparisons. If you did CO2 enhanced oil recovery, then you have to compare it to a world where you're not doing that at all. So it kind of details which I'm not going to go into. Again, the pathways here: polymers, methanol, methane, Fischer-Tropsch fuels, dimethyl ether, microalgae aggregates, cement curing, CO2 EOR, and cost of product made with CO2 utilization in US dollars per ton of product, median scoping review, various values here, selling price of product in US dollar per ton of product in the present day value. So again, you can see the comparisons here. So the percentage differences are shown as minus 30 here, plus 30 here in terms of cost of product made and selling price of products. So anticipated cost relative to incumbent in 2050. Summary, expert opinion, survey, and author group judgment is how these are estimated. Likely to be cheaper: polymers, methanol, insufficient consensus, methane likely to be more expensive. So you can already remember that now methane methane needs to be, so there is some global treaty made on reducing methane pollution. So you can see here the cost of product made versus selling price, the difference is 380%. And similarly for Fischer-Tropsch fuels, from syngas to diesel and so on, is plus 250%, and it's likely to be more expensive. And anticipated direction of cost relative to incumbent in 2050. Again, this is all mostly downward, except the CO2 EOR, which is expected to be upward in terms of the cost relative to incumbent in 2050. So it's likely to be more expensive here. So you can see maybe this is a better way of thinking about estimated CO2 utilization potential and break-even cost of different sub-pathways in low and high scenarios. The break-even cost is incentive measured in 2015 US dollar per ton of CO2. It always comes down to per ton of CO2 cost, whether you are going to penalize people for emitting, or you are going to estimate the cost for these various pathways of carbon utilization and removal, right? So that is required to make pathway economic. Negative break-even costs indicate that the pathway is already profitable without any incentive to utilize CO2, such as a tax on CO2 emissions in cases in which utilization avoids emissions, or a subsidy for CO2 removed from the atmosphere in the case of in which utilization removes CO2. So if utilization is just displacing and releasing it later, that's one thing, but if it is removing from the system for a reasonable amount of time, that's different. So utilization estimates are based on 2050 projections. Many technologies are in the very early stages of development, so the technology readiness level also has to be considered in these. For example, biochar is considered to have a low technology readiness level at this stage. And cost optimization via research and development could substantially change these estimates. So one has to always keep in mind these caveats. Color shadings reflect TRLs of the pathways, so technology readiness levels of the pathways, which again vary markedly within each pathway. Asterisks denote the storage duration offered by each pathway from days to months with 1 star, decades for 2 stars, centuries or longer for 3 stars. So just to point out, biochar, enhanced oil recovery, and forest urea, etc., are considered already profitable, but aggregates and BECS, methanol, methane, microalgae, cement, etc., have in the low scenarios and high scenarios have various levels of break-even costs in 2015 US dollars, and the non-conventional pathways like BECS, biochar, enhanced weathering, etc., are ranked here. So you can see again in the high case they have much higher estimated profitability or savings already. So polyols are here, biochar, enhanced oil recovery, methanol, forestry, aggregates, cement curing is still positive here, but it's much less here. So if it sequesters for multiple centuries or centuries and longer, versus other things like biochar, which is in decades, urea is just in days or months, right? So you can use CO2 to produce urea from methane, from ammonium, but once you use it, it's going to release that CO2 fairly quickly in days to months. So there is BECS with large range in gigaton CO2 utilized in 2050, and there are others in the high scenario, microalgae, methane, Fischer-Tropsch, and DME. Okay, so that's a kind of a quick run through, and it repeats some of the points we have made, but I hope you get the point that people do worry about the details of technical and economic prospects of carbon utilization and removal. And there are, despite these potentials and feasibilities that are estimated here, there are biophysical limits, which I will come back to in another paper. As I said, I'm just providing a very brief introduction, so you have to go and do your homework if you want more details with these kind of estimates. Okay.